Hello again. We continue with section 4, and this time we are going to study the phenomenon of refraction of waves. For this, we will see the phenomenon of refraction showing some experience that are familiar to all of us. Then we will do the mathematical formulation of the phenomenon of refraction obtaining Snell's law. And finally, we will see applications in devices that are familiar to all of us. When a wave arrives at the surface of separation between two media, generally two new waves are originated. The reflected wave that returns to the medium through which it has impacted, and the refracted wave that passes to a second medium, propagating at different speed. This phenomenon occurs whenever we have a separation surface between two media. As we already know, the perpendicular to the waves constitutes the ray. Therefore, we will have an incident ray, a reflected ray, and a refracted ray each time. In general, each time we find a separation surface between two media. But why does the velocity vary? It can vary either because there is a change of medium, as we have seen, but it can also change if the medium is heterogeneous. What happens when the velocity changes? Well, as we know, the period is going to be conserved since the frequency of it is not going to change. As the velocity is related to the wavelength and to the period through the expression we have on the screen, what will happen is that if the velocity increases, the wavelength will also increase, while if the velocity decreases, the wavelength decreases also. Well, let's see a simulation. Let's watch a video where we are going to show what we have discussed, and so it will be clearer. We are going to mark 3 points that are in the same state of vibration. If we have a wave that propagates with a medium where there is only one speed, the speed is 1.33 meters per second. The wavelength is the distance between the two red points, and therefore we have only one movement. What happens if we have a medium that is heterogeneous? That is a medium where there are two different velocities. Let us first consider that in the first medium. The velocity is higher, and that in the second medium the velocity is lower. Let's see. We see that in this medium the wavelength is this, while in the second medium, as the speed is less, the wavelength will also be less. This happens whether the first medium is the fast one or the second one. Let us now change the velocities, and let's check that something similar is observed. We're going to put a slightly smaller velocity, the same as we had before, more or less. Okay. Now the first medium corresponds to a medium with a smaller velocity. So the wavelength is smaller, while in the second medium the wavelength is longer because of the velocity. I think this makes it clear what we were trying to explain. Okay, well, Jay seems to be amazed. Let's see what he's astonished about. Well, it's because when you put the straw into the glass, it looks like this straw is broken. Completely broken. Well, what's wrong with him now? Because he's still just as amazed. Well, not only is it broken, but you have observed a position in which it seems that the straw is double. What is the specific reason for this? This fact is due to the fact that we have two refracted rays. Refracted ray 1 corresponds to refraction across the air-water separation surface, while refracted ray 2 corresponds to refraction occurring at the lateral curved surface. Since the normal to these surfaces is different, what we observe are two different images. Well, let's see if we can do the mathematical formulation. Refraction consists of a change of direction in the direction of wave propagation when two different media meet. After refraction, the propagating wave propagates in a second medium at a different speed. Well, we have an incident ray, and that incident ray forms an angle of incidence, which is the one formed by the incident ray with the perpendicular to the surface at the point of incidence. And we have the refracted ray, and an angle of refraction, which is the angle that the refracted ray forms with the perpendicular to the surface at the point of incidence and refraction, and will be this angle R. Okay, let us now consider a wavefront. At a given instant, a ray arrives at a point A. Any other point of this wavefront, for example B, is at a distance BD from the separating surface. If a distance BD is found from this surface when point B has reached D, point A has reached C, and this will occur at all intermediate points of this wavefront. We will therefore have a new wavefront, which will be constituted by all the points that join point D with point C. Distance BD is not the same as distance C. Why? Well, this is because although the time it has taken to travel the distance BD is the same as it has taken to travel the distance AC, the velocities in the medium 1 and medium 2 are different. It should be noted that the angle of refraction is also given by this new wavefront and the separation surface between the two media. By Hewen's principle, what happens? That when the ray hits or arrives at the point that we have called A, this new point becomes a new source emitting waves and will be each of the points that reach the surface. The envelope to these secondary waves constitutes the new wave front. Therefore, as we can see, the phenomenon of refraction can also be explained by Hewen's principle. Let's see the mathematical formulation of this phenomenon. Well, let us consider the sign of the angle of incidence taking into account the triangle ABD. The sine di can be expressed as the opposite leg BD divided by the hypotenuse, which is AD. The distance BD will have been traveled in a time t, and the velocity in that medium is VI. Similarly, if we express the sine of the refracted angle taking into account the triangle ACD, we will have that the sin of R will be equal to AC divided by AD. This distance AC is traveled, as we have already said, in the same time as the distance BD, and therefore AC will be the propagation velocity, which is VR times T. That is AC divided by AD. Note that this distance AD is the same in both expressions. Therefore, if we clear and equalize, we have a relationship between the angles of incidence and refraction as a function of the velocities of the first and second medium. This constitutes Snell's law of refraction. Now, what are the laws of refraction? First of all, the angle of incidence, the refracted angle and the normal to the surface at the point of incidence are in the same plane. Secondly, Snell's law, which gives us a relationship between the angles of incidence and refraction and the velocities of propagation in these media. And finally, the index of refraction, which is a parameter which in this case is a relative refractive index of medium 2 with respect to medium 1, and can be expressed as a function of the velocities of the ratio of the velocities between medium 1 and medium 2. Well, what are the related subjects? Well, the lenses, the glasses, are a direct application of the phenomenon of refraction. And what devices use lenses? Well, first of all, our eyes. Our eyes are lenses and therefore make use of the phenomenon of refraction. Of course, so does the magnifying glass. We see that when we see an image, the surface of the horizon is seen as split. That is the same, similar, better said, to what we had seen with the subject of the straw in the glass. And of course, the microscope. The microscope is a device that uses lenses and that, based on the phenomenon of refraction, has allowed us to obtain many scientific advances. And in general, any device that makes use of lenses. What other phenomenon can we relate to refraction? Well, it is the formation of the rainbow. Why does the rainbow form? Rainbows are formed by the scattering of light as it refracts off raindrops suspended in the air. You see the spectrum of colors whenever we look at an area with the sun behind us in an area where it is raining. What have we seen in this topic? Well, we have presented Snell's law, seeing that it is a relationship between the angles of incidence and refraction, and the velocities of propagation in these media. We have also seen the relative refractive index of a medium 2 with respect to 1, which is a function of the velocity ratio. And finally, we have seen applications that make use of the phenomenon of refraction. That's all. See you in the next class.